Yes, I will talk about the interface instabilities of growing hydrides. I will also talk a little about the cracking that appears in the hydrides as they grow. This was prepared by myself. No, sorry. By. Oh my God.
Crazy devices.
Yes. Too many buttons. And my colleague, Ugo Liljeman, and we are from the university in Sweden. And now I get work here. This is the experiment. It was not done by us, but the setup is like this. You have a zirconium metal plate, and it's heated. And then there is a device outside that makes a cold spot on the surface of the plate. And it's also, the zirconium plate is charged with hydrogen, and the thing that happens when you get this cold spot, you get the temperature distribution and the hydrogen starts migrating towards the cold spot. And when the concentration is enough, it starts reacting with the zirconium and forms a hydride. This is a picture of the hydride, seen from outside, and you can see some dark lines in it. And this is a cross-section. You can see a crack, so these dark lines are cracks that go down through the hydride. And it's called a blister because it's bulging out like this. I forget to say also that this is very close to engineering practice. Zirconium is used extensively in nuclear power plants, and it's holding together the fuel pellets. And you don't want to have a hydride in there because the hydride has very poor fracture mechanical properties. It's almost like a biscuit. Still, there is a controversy of why it cracks, because people say there ought to be compressive stresses in this material because it expands about 20% volumetric percent, so it's a lot of expansion, and it puts certainly a pressure on the outside. And I will focus on two things, the crack and also this beard-like region surrounding the hydride. And to do so, we use a phase field model. And in the phase field model, it's like normal physics, but the phase field model means that you add a parameter or a variable that keeps track of the phase. So here, in this case, we choose 0 for psi in the zirconium and 1 in the hydride. And then there is an intermediate region where psi is between 0 and 1. So to get some equations from this, we start with Gibbs free energy, and in our case we have included the elastic energy, and we have included a chemical potential and the gradient energy. And elastic energy, you recognize this. This is the potential, chemical potential that I will show you more of soon. And this is the gradient material. This one is responsible for diffusion. This one is responsible for keeping objects together, so they are opposed to each other. And they are depending on psi, and so is also the strains. These are the total strains, and they include the expansion that is due when the material becoming a hydride. Now this is the chemical potential. It was suggested by Landau in the 50s. And it's the simplest you can think of. It has two minimum, one minimum for psi is equal to 0, where you have zirconium. Then there is a barrier, and then you have a minimum also for the hydride. And when the concentration goes of the molecules goes up and come on this side and then spontaneously form the hydride. This is the swelling of the material. That is 0 for zirconium and maximum for the fully developed hydride. Now, in order to get the differential equations out of it, we use a proposal by Ginsburg and Landau, and this package here is the variation of the total free energy with respect to the variable. Here is the phase, and then you get the rate of change of the phase, and this is for displacement, and it looks the same. And this is just a positive proportional constant. And if you just put previous equations together, you end up with this. This is also non-dimensionalized. So from the beginning, you have 7 constants, and they disappear into making this dimensionless. And there's only one free left. But if we start with the mechanical part, you can recognize this as the Navier's equation that controls deformation. And this is a term that you have to have if you have expansion. And this equation that controls the phase looks a lot like Fourier's equation or Fick's law or for diffusion or temperature, but here is for the phase. And you have a right-hand side. If you, for a moment, think of the temperature instead, so put T here and T here, then this becomes Fourier's law, right? And the right-hand side is the heat source, distributed heat source in the body. And if you do that, then you can use any or most general-purpose finite element codes just by pretending that this is temperature, heat source. And in Abacus, for instance, there is an element for fully coupled thermal stress analysis. And this is it, because the swelling here depends on psi. And here you have the elastic strains that comes from this equation. So it's fully coupled, but you have the element. The only thing you need to do is program this part and this part, and it takes like 2 hours to produce, if you're familiar with Fortran. So then we need a calculation for a flat surface. This down here is supposed to be the hydride. Up here you have the zirconium, and you have an interface in between. And there is some variations here. It's noise added to the surface, but if we didn't have the noise, it would just widen about this much, and then the hydride will start growing because we have exceeded the limit for when the hydride grows. With a lower strain, it will go the other way. But this noise makes a variation that has a certain frequency, and you can see it grows, becomes like fingers, and grow and grow and grow outside the mesh. We worried about the element size, if that was triggering this frequency, but we double the element size and nothing happens. We make it half, nothing happens either. And so this is the pattern, but if you vary the material parameters, then things change. In the classical analysis, without this interface and the phase, just a sharp interface, you would have a surface energy instead, and that can be calculated from the parameters that we're using. For a flat surface, this is the exact value. And the strain energy. And whatever happens at the surface that changes the morphology, and you see a frequency or a wavelength in there, it's very probable that it's the ratio of these two that gives the length scale. So this would be the length scale for the fringes and how many you get over the surface. If you look here, if we changed, nothing really happened to this. If we maintain the ratio, but if we only increase the surface energy, then you will see twice as, or only half as many, so maybe 2 over this size. And if you change the length scale, then you're back again in business, and you get things similar to this. So that was about the fringes that are over here. No, these are not really fingers, but we believe that it could be the reason that it's unstable surface and these threads are sticking up. Now over to the crack. This is a different experiment. We found around 10 different groups who made experiments like this, and almost all of them get these cracks. And almost all of them say it's a mystery, because if you have compression, then there shouldn't be a crack, right? You get tension, then you get rid of the tension because you get a crack instead. So that is what should have happened. But they think of, the Eshelby solution and the Hill solution with plasticity of an inclusion that is expanding, and if you think of all of this and you expand it from 0 expansion and you increase the expansion to the 20%, that is the end of this, then there will be compression everywhere, but that's not what happens. What happens is that you have a small blister from the beginning, the blister is fully expanded, but it includes layer by layer of zirconium and includes it in the hydride, and when the zirconium is included, it expands. So because of that, you get also plastic deformation outside the hydride when it's small, and all this area, when you come to this state here, all this area is filled with residual strain from the expansion. So we did this earlier just for a straight surface. Now we did it also for phase field, and we found an analytical solution for this incremental increase. Here's the center, and this is a sphere. Here's the center of the sphere. Here's the boundary towards the zirconium. And stress, the tangential stress increases, and then it drops in the plastic zone, and then it drops. And in each solution, it's constant over here, constant pressure. But if you consider that it has been growing similarly since it was very small, you get increased stresses, and then you get tensile stresses in the middle, and actually this is a logarithmic singularity. It's hard to believe, but it's a logarithmic singularity, and you get very high stresses in the center. And this is done also if you do something analytical, you are afraid that maybe you have a pi missing or a 2 or so. So finite elements, it's a comfort that they almost exactly coincide with the analytical result. Here's an effect of the element size. And with phase field, we get similar result, and it also drops stress, and it increases, and here's probably insufficient element size. So that was for a sphere. Now for a blister, we thought that maybe that's the thing also for the blister, and it could be, but it's not that much. That's before. So if you follow, this is the blister, you see it bulking out. If you follow a trace from down here and up to here, you can follow the tangential stress. It increases, becomes compressive, and then you have some tensile stresses at the surface. So conclusions are, a stretched surface is unstable. Surface develops fingers, and the surface energy and strain energy gives the length scale. Spherical precipitates actually develops large stresses. Stress singularity was from the analytical solution. And the surface blisters may crack from tensile stress. Thank you.